In this video, I'm going to present you the conference paper Design and Evaluation of Interaction Techniques dedicated to integrate encounter-type haptic displays and virtual environments. This paper has been done with the contributions of Victor Mercado, your presenter, Maud Marchal, and Anatole Cuye. Let's begin again with the basics. What are encounter-type haptic displays, or ETHDs? In very simple words, they are hi-fi robots. Needed for attention, these systems follow the user hand position, holding their end effector and hoping for users to encounter it and give the high five. ETHDs provide users the advantage of not wearing an actuator that renders haptic feedback below their skin. This permits users to engage and disengage contact with a surface that the ETHD system provides. While the premise sounds exciting, there are several challenges to overcome, such as rendering a large contact area, avoiding lag, and also avoiding unexpected collisions with the user. The contributions of this paper are a design space for interaction techniques dedicated to ETHDs. 5 techniques were conceived from the design space to address ETHDs issues, namely swipe, clutch, drag, bubble, and follow, a use case scenario to contextualize the conceived techniques, and a user study to assess their performance. So let's talk about related work. To evaluate the interaction techniques used for ETHDs, first we need to consider the type of contact area that they provide. On one hand, we have static contact area rendering. This means that the users cannot displace the contact area once they have engaged contact with the surface brought by the ETHDs. Most of the work done by the ETHD community falls into this category. Having a static contact area can lead to a complete object surface representation, meaning that the user can touch the entirety of an object represented in a virtual environment, such as the work of Abtahi et al. And we also have the classical partial object surface representation, such as the work of Araujo et al. But we can also have a movable contact area, such as the cases of Whitmer et al. And a previous work where the ETHD displays the contact area once the user engaged contact with the physical surface. Having an ETHD that provides a complete optic surface representation is a hard task to achieve. Thus, most of the works concerning these types of haptic displays have a limited contact area, mainly for 2 reasons. The first is the size of the tangible object being held, and the second is the ETHD's mobility range. To the best of our knowledge, there's limited work in matters of interaction techniques that could exploit both tangible object size and ETHD workspace in order to render a large contact area. And now the interaction techniques. Before conceptualizing the interaction techniques to address the ETHD's issues, we created a design space that takes into account parameters present in ETHD interaction, namely input, movement control, displacement, and contact. The first parameter, input, refers to the method in which users can provide instructions to the system. We consider 2 options, input by gesture recognition and controller input. The second parameter, movement control, refers to whether the users need to manually tell the ETHD system to go to a new position or that the system automatically calculates a new position based on previously given input. Thus, the 2 branches considered are manual movement control and automatic movement control. The third parameter, displacement, refers to whether the displacement from position A to position B can be achieved in one single movement. This means absolute displacement, or gradually as a step displacement. The fourth parameter, contact, refers to whether the users need to keep in contact with the surface or not when instructing the system to go to a new position. And now we have our design space representing the combination of the different interaction parameters. As you can see, we discarded the combinations between controller input and automatic displacement, since this will mean to totally control the robot movement, which does not follow the ETHD principle of user tracking and displacement. For conceiving interaction techniques, we decided to explore at least once each of the different branches provided by the interaction parameters. The first technique, swipe, is a combination of gesture input, manual movement control, step displacement, and out-of-contact command. The second interaction technique, drag, is a combination of gesture input, manual movement control, absolute displacement, and out-of-contact control. The third interaction technique, bubble, is a combination of gesture input, automatic movement control, step displacement, and in-contact control. The fourth interaction technique, follow, is a combination of gesture input, automatic movement control, absolute displacement, and out-of-contact control. The final interaction technique, clutch, is a combination of controller input, manual movement control, absolute displacement, and out-of-contact control. The scenario where we integrated the interaction techniques is a virtual desktop where the users are prompted to paint with their fingers in a canvas with different figures. The canvas is way wider than the contact area, so the users need to displace it properly to complete the tasks. Let's see the interaction technique in action. The swipe technique. As you can see, the user needs to perform a swipe to move the contact area. This area is going to move depending on the direction of the swipe. The system detects the swipe gesture and discards the spilled paint during the process. The clutch technique is the only one requiring control input. Users press the Vive controller's trigger to activate an auxiliary contact area that indicates the next area to be touched. After the selection, a visual aid will appear to indicate the users to wait until the next contact area is rendered so they can touch it one more time. The drag technique is very similar to the clutch, but this one only requires a gesture input. Users need to elevate their finger to activate the auxiliary contact area to select the place that they want to touch next. The loading visual aid appears to instruct users to wait until the contact area is fully rendered so they can engage contact one more time. The bubble technique works as a steering wheel. Users need to touch the border of the contact area to displace it in a required direction, as you can see here. The follow technique involves constant following of the user's finger. It is activated when users raise their finger and move it outside the contact area, and it is deactivated when users engage contact again with a physical prop surface. The system setup of the use case scenario is integrated by a universal robot's UR robotic arm that holds and displays the tangible surface, an HTC Vive to render the virtual environment, and a byte tracker to locate the user's finger. Users were equipped as well with a headset playing white noise in order to isolate them from the robot's noise. The system integration was done in Unity game engine. Now let's talk about the user study and how did we evaluate the interaction techniques. The objective of the user study was to evaluate the design technique's performance in rendering a white flat surface. The experiment was divided into 5 blocks, one per interaction technique. Each block was divided into 4 trials, 1 training trial and 3 experimental trials. All of the trials had a maximum duration of 4 minutes. The collected data in this experiment consisted on the elapsed time for each trial, interior shape coloring percentage, exterior shape coloring percentage, or in simple words, whether the user spilled paint outside the shapes or left uncolored spaces, and a painting error percentage. We also evaluated the user experience with a questionnaire using a 7-point Likert scale. We gathered a total of 20 participants, 6 female, 14 male. Results were in favor of the clutch technique, who took the lead in the quantitative results. Second places were distributed between the rest of the interaction techniques, except for swipe. This presents the average value and the standard deviation in parentheses for all the interaction techniques and collected quantitative data. We ran a statistical analysis and found significant differences between several combinations of the techniques. For further information, please consult the paper. Concerned collected qualitative data We ran an analysis of variance of the user experience features that pointed out a significant effect on the interaction techniques for 5 criteria: controllable, captivating, motivating, easy to learn, and fast. We also conducted a statistical analysis and found significant differences between several combinations of techniques and user experience features. Results from the user study and participant comments point out several factors to be considered. For instance, participants commented that the visual feedback provided by techniques permitted them to understand how the system was performing so they could know when and where to touch. The visual feedback was useful for addressing the lack and safety issues of ETHDs, since it provided visual feedback, of course, to the users about the system status. The techniques with the highest performance, in this case drag and clutch, were those who had a controlling gesture weight different to the coloring task. On the other hand, the bubble and swipe techniques obtained the highest error ratio because the control gesture was too similar to the painting task. The drag and follow techniques were the slowest one because probably to the influence of the fit slow when putting and selecting a new contact area. Additionally, we have to take into account the complexity and proximity of each shape to the user as a factor that influences the user performance. In conclusion, we created a design space based on 4 interaction parameters such as input, movement control, displacement, and contact. This design space serves as a tool for conceptualizing interaction techniques for ETHDs, such as the one created in this paper to address ETHDs limitations. In total, 5 techniques were conceived: swipe, clutch, drag, bubble, and follow. The techniques created represent at least one branch of the interaction parameters. A use case scenario based on a finger painting task was created for contextualizing these techniques and also to evaluate them in a user study. Results pointed out that the preferred techniques were clutch and drag in quantitative and qualitative data, respectively. Future work can consider to test 3D surface rendering for the proposed technique, as well as an evaluation of the effectiveness of this technique for rendering a large contact area. Future work can also consider the exploration of other combinations of the current design space or the inclusion of new interaction parameters. New use cases can also be conceived from these techniques and from the design space as well. Thank you for your attention. If you've had any questions, do not hesitate to ask.